Okay, here's where we were last time. We were talking about doing change of variables. In particular, we were talking about how to use the polar coordinates conversion formulas as a change of variables function, which is a clever idea, right? It's not what we wrote them down for in the first place, but it works. It is a change of variables function. We know the stretching factor. You can totally do a pullback through the polar coordinates conversion formulas. It's a neat little trick. So this is where we ended last time, and we had talked about how you could take that conversion formula, change of variables function. You could pull back. Right? You could identify what this new pullback domain is, and you could then slice up that pullback. And then we decided, well, golly, that's a lot of trouble, right? To have to actually draw the pullback. Why should we bother drawing the pullback when we can see what these slices look like over here in the XY plane where we already had a picture of our domain? And, well, it's just like this. This is what those slices look like over here in the XY plane. And so no particular need to draw this picture and slice it up this way. I can just keep my picture and slice it up that way. It's just convenient. So this is what we call doing an integral in polar coordinates. That's just code for pulling back through a change of variables but observing my slices as they appear in the XY plane. Okay, so we're going to see a bunch of examples, basically. And then we're going to do the same thing for cylindrical, and then we're going to do the same thing for spherical. And it's all pretty much the same ideas, just sort of different geometry. Okay, so here we go. Let's suppose that my domain is the unit disk, like this. All right, so what do my slices look like? And keep in mind, a slice is where you, do like that. The slice as it applies to this unit disk looks something like this. Where's the first one? Where's the last one? Well, the first one, arbitrarily, you don't really have to start at theta equals 0, but you kind of might as well. And then they just keep going. They go all the way around. And once you get back to where you had been, you're done. You've swept out your entire domain. And so you stop. And now, of course, it's tempting to say, well, if I'm back to where I had been, isn't that the same value of theta? Well, no, because my theta is increasing the whole way around. So I've done a loop, and so we started at 0, we end at 2 pi. It's not 0 to 0. That's boring. Okay, so 0 to 2 pi, and there's the 0, and here is orange. Here's my 2 pi. Is everybody on board? Okay. All right. Now, for a particular slice, looking at a particular theta slice, let's now ask what's the range of values of r. Well, r, there's the sort of the first value of r, right? And that's at the origin, where r is obviously 0. I don't have to play any fancy games there of identifying a particular curve that it's on and solving equations and stuff. I can just kind of straight up see that r is equal to 0 there. And then likewise, where's my last value of r? Well, it's there, which is on this curve. And being as this is the unit disk, conveniently, I know what its distance from the origin is. It's the unit disk. This distance from the origin is 1, and that gives me 1 as my upper bound. Is everybody happy? Okay. Alrighty. And then, yada, yada, yada. So details, computation, make sure you can follow those details, of course. Okay. Before we go to the next example, here are some tips and tricks that I think are really useful. It turns out it's practically always best to go in this order here. Always dr on the inside, d theta on the outside. I guess I shouldn't say always. There are some weird, manufactured, unnatural counterexamples. But in practice, in the real world, what you're going to see most of the time in practically all cases, this is the best order. So for all intents and purposes, you might as well just always slice in this order. Okay. The other thing I want to say about your sort of differentials is when you write them down, when you write down your dr d theta, please don't ever just write them down as dr d theta. You're never going to have just dr d theta. It's always going to be r dr d theta because r is your stretching factor, right? And when you're doing a polar coordinate integral, you are doing a pullback. You are doing a change of variables. You will always have that there. Right? So here's the problem. A lot of students write down the differentials thinking, look, I'm worried about my bounds. How do these cross sections look and what's the geometry here? And they're thinking about all of that stuff, all very reasonable, all very understandable. But the problem is that when you get distracted by all that stuff, it's so easy to forget to come back and just stick in your stretching factor. Right? So I think it's a much healthier idea to, as you write down your differentials, also at the same time, all at once, write down r dr d theta. Then you can't forget it. You already didn't forget it. Right? So I urge you to do this. You don't have to, but I urge you to do this. The stretching factor, after all, this is the most multivariable calculus of the various different ideas that go into one of these kinds of problems, is that stretching factor, understanding how this is a change of variables problem and how the stretching factor is integral to sort of recognizing that sort of conversion. So that alone, just r dr d theta, is worth several points on let's say a 20-point question, for example, right? So get those easy points. Get them early, right? Don't accidentally forget to get those easy points. Okay. All right. And then, of course, we have our usual sort of, multi-step process for finding the bounds on our iterated integrals. The bounds come from certain points that we identify as coming from certain curves that have certain equations in which you just solve for the bounds that you need. It's just like every other kind of integral that we've done previously. And now let's see a bunch of examples. Okay. So suppose you're doing an integral on this, what we call an annulus. It's like a ring. I like to think of this as being a moat around a castle. I don't know why. That's just where my head goes. This is tempting to rewrite as being an integral on this purple region subtracted off of an integral on this larger red region. Right? Tempting to take the whole solid disk and subtract off the inside purple disk, and then the blue moat would remain. Right? Very tempting. Doesn't work. It doesn't work because if you look carefully at our integrand here, our integrand has a problem. Our integrand is undefined at the origin, right? So this point right here, you cannot define that integral at the origin. That means that the purple integral is undefined. You can't compute it because it's not even defined. Likewise, that green point is part of our little red thing, so that's undefined as well. So if you want to approach this blue integral around the annulus as given, this whole idea here, clever move, doesn't work. Everybody see that? Okay. So what do we do? Arguably a second attempt could be to, let's just kind of slice it up in the usual sort of rectangular way. And, of course, this is catastrophic, right? You'd have that region, and then you'd have this region, and then you'd have this region, and then you would have this region, and you've got 4 separate integrals, each of which is a nightmare because it has square roots all over, just riddled with square roots. Right? So catastrophic, don't even think about doing it that way. That's terrible. Okay. Much easier Polar coordinates. This question is made for polar coordinates because the polar coordinate breakdown is just very straightforward. Theta goes all the way around. So 0 to 2 pi. Just like the last one we saw. And then you can focus your attention on a single value of theta, like so, to find your r bounds. The lower bound for r is going to come from that point. That point is on this curve, which has this equation, in which, and wait a second, I'm looking for a value of r, so I need to solve for r in that equation, conveniently already solved for r, and there you go. There's your lower bound of 1. Everybody happy with that? All right, so let's see. Our upper bound for r is going to come from this point, which is on that curve, which has that equation. Again, lucky break already solved for r. Our upper bound is 2. Everybody good? And everything works out just fine. Now, you will also note, I guess I kind of glossed over this part, you will notice that when I wrote down my differentials, I wrote down my stretching factor at the same time. Thankfully, right? Because I had to draw my picture, I had to think about the geometry. I totally could have forgotten that r if I hadn't written it down as at the same time as, I mean, after all, by the way, this r dr d theta, that is your dx dy. Right? Dr d theta by itself isn't really particularly meaningful in this question. R dr d theta is the dx dy that I actually care about. So that having been remembered, I can then note that our integrand here is just 1, which is very convenient, and that as an world's easiest integrand, and you crank it out, and here's your final answer. Yeah?
Sorry, how'd you get the 1 over r?
Oh, yeah, thank you. That is from the statement of the original integral that we're interested in. Our integrand is 1 over square root of x squared plus y squared, and that's just writing it in polar coordinates. Yeah, totally. Everybody happy? Okay, another example. A little bit less convenient of an example. We've seen a couple of examples where there's, basically circles centered at the origin. That makes for sort of nice, easy equations. The geometry of this one's going to be a little bit different because there's some stuff that's kind of off-center, and the algebra is going to be a little bit less convenient accordingly. But still, basically the same ideas. So here we go. We're computing an integral. We have a region given. The region is this weird thing right here. It is, let's see here, we're going to look for this disk, and then we're going to subtract off, that's what this sort of backslash means, we're going to subtract all of these points in this disk. And what do you get when you take that big red bite out of that purple disk, and what's left over is kind of a little solar eclipse? Just to make a call back to last week. It's something about like that. Is that cool? All right, so let's think about how to do this. A couple of freebies first. Notice the formula for x in polar coordinates. You could view this as we're pulling back that algebraic expression through the polar coordinates conversion formulas, or you can say it in straight English. I just got to figure out how to write x in polar coordinates. And that's a known standard formula, so nothing to it. X is r cosine theta. Okay. dA, otherwise known as dx dy, r dr d theta. Right, again, very natural to stick in your stretching factor r as you're writing down the dr d theta, because that's what dA is. Right, so again, really weird and unnatural to write down dr d theta and to pause on writing that down until you've done other things. It doesn't make any sense, right? So just go ahead and write it down while you're at it. Okay, and now the bounds. Let's think about our theta bounds. Theta does not go all the way around. There's a theta slice. How that actually looks on our little eclipse solid here is about like that. And for higher values of theta, they look kind of increasingly like that. And then for lower values of theta, they're increasingly kind of like that. And let's talk first and last. The first one is at that point. A little, corner down there. You can find this in a couple different ways. If you want to write down the equations for the two curves, fine, totally cool. However, sometimes you get really lucky with the geometry, and when there's lucky geometry, I encourage you to go ahead and capitalize on that. And here's the lucky geometry. Check it out. This and this are both radii of a circle that we know has radius 1. So that makes that length and that length 1. And then furthermore, let's see here, this edge right here is a radius of that circle of known radius 1. That makes that edge 1. Right? And so very conveniently, just a couple of quick geometric observations. I see I have an equilateral triangle there that instantly tells me what that angle is, and that pretty much immediately tells me that this value of theta minus pi over 3. Everybody happy? Okay. Analogously, the ending value of theta, whoops, I missed, positive pi over 3. There's a similar little equilateral triangle up there. Okay, convenient. Okay, now we look at a given theta slice. So for that given value of theta, where does R start? R starts at that point. That point is on this curve. That curve has, wait a minute, where is that curve? That curve is going to come out of this inequality. In particular, it's the boundary of that inequality, and that's in rectangular coordinates, but I need this in polar coordinates. It turns out that that's just R equals 1. Again, pretty straightforward, a little bit of algebra. That gives me my lower bound for R. Then analogously, there's my last R slice. That point is on this curve, which has, it has an equation that's going to come from here. Again, you have to look at sort of the boundary of this. That's where you have an equality here. That rectangular equation, not as obvious. Here you're going to have to actually kind of crank a little bit and figure out how to convert this into polar coordinates. And when you do that, that's chapter 1 stuff, right? When you convert that into polar coordinates, you're going to get that. And therefore, that is our upper bound for R. Is everybody happy? Okay. All right. All good on this one then. Moving along. This is a tricky and weird one. Actually kind of historically important. Some of y'all may have had a class in statistics, or some of y'all may have taken a Calc 2 class here where we spent a little bit of time talking about applications of single variable calculus to statistics. And big idea is there's this thing called a probability density function, and the way you compute probabilities from a probability density function is with an integral. So we very often find ourselves integrating functions that define probability density. And that's actually exactly what this is, sort of. And in particular, this is all except for a certain constant, pretty much what we mean by what's called a normal distribution. And it turns out normal distributions are extremely important in very powerful and natural ways in statistics. In some sense, in the limit, when you repeat any random variable n times and let n approach infinity, the limit of the distribution is always this little weirdo It's very surprising how that works out. But anyway, very important in statistics. So we need to be able to compute probabilities. We're related to that going to need to know the value of this integral. And here's the bad news. You cannot find the antiderivative for this function. You just can't do it without power series, which nobody wants. Right? You want a closed form, answer. So how are we going to compute that integral if we can't find its antiderivative? It's a tough one. So here's the really clever idea. This is super clever. I did not think of this. Somebody showed me, whatever that's worth. I'm going to compute J, just calling it J, by instead computing J squared. Now, it doesn't look exactly like I've written down two factors of J here. One of them looks like a J. This one looks a little different. I've got a different dummy variable in there. But I claim the dummy variable doesn't matter. Right? Whatever you do with the Y is going to just, as we say, integrate out. Right? And whether I call it X or Y or P or Q or Bob, it doesn't matter. It's just a dummy variable. This basically is just a tool for allowing me to write down that I want to find, speaking casually, the area under a certain curve. And what I use for my variable doesn't change the shape of the curve. Okay, so that is J squared. Now, recall, if I'm interested in this Y integral, this thing here, this X integral, it is in fact just J. It's just a number. I don't know what it is yet, but it's just a number. It's not a variable. It can't equal to a bunch of different things. It's just a single value. It's a constant. And constants you can move inside of an integral. Right? Weird that I would want to do that, but legal. Okay. All right, now that said, now let's look at this integral. Recall that when you have an integral outside of an integral, the variable furthest to the outside is a constant. That means that in this case y is a constant, and therefore e to the y squared is constant. And again, constants can move inside of the integral. Now, this is a couple of weird sort of like folding inward of something of the expression, but perfectly legal. And what I have then is that this thing, J squared, that I'm interested in is this iterated integral. And that's just a regular old, plain old section 5.3 style iterated integral. And then I'll remind you, iterated integrals are double integrals. So who cares? Right? What have I done so far? One could argue that what I've done is I've turned a question that I don't know how to answer into a seemingly harder question that I also don't know how to answer. Weird cultural point about math. Sometimes taking a question and reinterpreting it as a harder question actually makes it easier. Weird things happen sometimes. What happens here in particular, because this is now a double integral, I have multivariable calculus techniques that I can apply to this double integral that don't really exist in the single variable context. And in particular, because this is a double integral in the xy plane, I can write that double integral in polar coordinates. And notice that's all that's happened here. Just polar coordinates. dA, r dr d theta. Same move that we did with all of our other polar integrals. Let's see here. X squared plus y squared, r squared. Old news. How do I describe all of R2 in polar coordinates? Well, I'm going to take every possible angle, and for every possible angle, every direction coming out of the origin, I'm going to start at the origin and go all the way out to infinity. That gives me, for these variables, r and theta, every possible point in R2. So I haven't really done anything yet. I just observed that this product is an iterated integral, which is a double integral, which I can compute in polar coordinates. Still haven't really done anything yet. Okay, and with that observed, check it out. This is now an easy single variable calculus question. Because if you look at that inside integral, this is where we, sort of hit the wall when we were thinking about, up here at the top, and I can't find an antiderivative of e to the negative x squared. Well, there it is. There's the ugly e to the negative whatever squared. How do I find an r antiderivative of that? Oh, I don't have to. My integrand is actually e to the negative r squared times r. And this extra factor of r makes this an easy integral. It's just a u substitution. Let u equals negative r squared. Boom. So I'm going to leave the details of that to y'all. And it's a good, healthy exercise to make sure that you still remember how to do improper integrals and that you still remember how to do substitutions and stuff. And it's a nice, like I say, a little healthy exercise. Everybody should do that once in their lives. So ends up that the answer is pi. Yeah.
So in the third step,
yeah.
You move the e to the minus y squared. Can you move that into the x integral because y is technically constant?
That's exactly it. Yep, that's right. So y is further to the outside. And so while I'm computing that x integral, y is not changing.
Okay.
So yeah, that's exactly because it's a constant that I can toss it in there. Yeah. All right. Okay, so neat fact. Now, just to avoid spiking the football on the 2-yard line, what did I just compute here? I just computed j squared. Remember, our actual original question was to compute just j, and so that's square root of pi. It's easy to forget that last little bit. So anyway, final answer, square root of pi. Okay, so let's, as previously promised, do the same thing now in cylindrical coordinates. We've already observed that you can view cylindrical coordinates as a change of variables function. We've already computed the stretching factor. We could totally do pullbacks. We would regret the artistic challenge of having to draw the pullback. And in order to avoid that, let's try to instead ask, what does it look like if I take, for example, a theta slice like that, a constant value of theta? What does that look like in XYZ world? And, well, it just represents what I like to call a half plane hinged on the z-axis. Just to discuss that language a little bit, to me, I feel like this is like a door that's kind of can swing. As I look at different theta slices, this door kind of swings like a door on a hinge. The hinges would be on the z-axis. Everybody cool with that? Okay. You could do the same thing for R. Just keep in mind what an R slice is. An R slice just says I'm going to look at constant values of R, and a constant value of R in XYZ world is just part of a cylinder. Something like that. It's going to turn out we're actually not going to have much need for this picture. Anyway, if you wanted to do that, that's how you do it. Okay, so we're going to do some integrals and cylindrical coordinates now. Before we get started, just again, a couple of convenient facts to know. Good news, of your 6 different options for how to order your differentials, there's basically never, technically speaking, any call to do anything other than these 2. So I encourage you to just always pick one or the other of these 2. We'll talk about how to decide between these 2 in just a second. But notice what defines what these 2 options are. You always want dr and d theta together and in the usual order with dr on the inside. And then there's only 2 ways to do this. You can either have dz on the outside or dz on the inside. So that's how you remember what these 2 options are. How would you decide between these? Well, again, keep in mind, it's a question of what are you going to solve for in terms of what? Notice if you choose this first option, you're going to need to solve for r as a function of theta and z. right? On the other hand, if you choose this other one, you're going to have to solve for z as a function of r and theta. So which would you rather solve for, r or z, is basically going to answer your question of which way you'd want to choose between these two options. And of course, it depends very much on the actual solid that you're dealing with, and look at the equations involved, and well, which one of those do you want to solve for? All right, so then everything after this is sort of as before. Again, don't just write down your differentials. Your differentials by themselves don't mean anything. Volume, dV, requires the stretching factor. So go ahead and stick that in there. Don't forget your stretching factor. Again, that stretching factor alone is going to be worth several points on the exam. Just write it down. So easy. I made this observation to one of the earlier classes. If you find yourself with 10 seconds left to go on the exam, just having started one of these questions of, compute the following integral, just writing this alone down will get you several points. So just write that down. Right? Don't make the mistake of thinking, hey, I'll come back and remember to write down that stretching factor later. It's based on my previous experience, I'm going to say about 1 chance in 3 that you'll forget. I've seen it so often, right? It's a catastrophe every time. It makes me cry just a little bit. So just write it down when you write down your differentials, and then you won't forget. You already didn't forget. Okay. All right. And then, again, our usual process for how to find bounds. We identify the relevant points. We see what surfaces they're on. We recognize that they have certain equations, and then you solve. Okay, let's get our hands dirty. Here is an example. And let's see here. We have the upper half ball here. Let's see here. This shape right here. And let's think about how to slice that up. Now you'll notice that the very first thing I've done here is I have rewritten my dV. Notice I already didn't forget my r. Right? dV, dx, dy, dz is absolutely not the same as dz, dr, d theta, but it is the same as r dz, dr, d theta. So this comes from that. And again, write it down all at once. Okay, the integrand, well, that is what it is. I don't want to get distracted by that. That's just, again, sort of plugging in, rewriting things in cylindrical coordinates. That's algebra from chapter 1. Y'all can do that. I just left that ambiguous here. But now, let's work on finding our bounds. We will start with our theta bounds. Notice I chose one of my two options of how to order differentials. We'll look at the other one in just a second. Arbitrarily, I'm choosing this one. And let's see here. Theta, here's what a theta slice looks like. Geometric appeal, this slice of my ball will make this thing right there. Kind of a quarter disc. Does everybody see that geometry? Okay, so first and last, and I could argue that the first one might as well be viewed as being right here, where theta is equal to 0. Yeah. And then theta is going to go all the way around. And then the last one, it's just like with polar coordinates, the last one's going to, for this particular solid anyway, is going to be when I get back to kind of where I had been, which those colors combine in a weird way, but 2 pi. So theta goes from 0 to 2 pi. Is everybody good? Okay. All right, now we focus our attention on that slice. We're going to fix theta then. Now we're going to look at r slices. Here's where I'm going to flash back to what we already said about our r slices. What does an r slice look like? An r slice is a cylinder or part of a cylinder, kind of like that, representing a given constant distance away from the z-axis. So what does that look like on our theta slice? Keep in mind, I'm not actually interested in an r slice of my solid. I'm only interested in an r slice of my theta slice. And so I need to know, how does this green thing intersect with that purple cylinder? And, well, again, geometric appeal, the way those intersect is just on this kind of line segment right there. Everybody see that? All right, so just to clean up the mess then, there is my r slice of my theta slice. And so again, I got to play games with first and last. So what's the first r slice? Well, the first r slice on this theta slice is there, where r is 0. And so my lower bound for r is 0. Where's my last value of r? Okay, now this you got to think about. Here again are my r slices. My r slices continue. You'll notice they kind of get shorter and shorter and shorter as I approach sort of the edge, and then the last one is going to be where I get just this point there by itself. And what can I say about that point? A couple different ways you can approach this. You could observe that this point, it's on the sphere, it's on the xy plane. Write those down, solve for r, and you could get an answer that way, and that's totally fine. But again, sometimes you get lucky with the geometry. When you get lucky with the geometry, capitalize on that. In this case, notice that this distance that I'm looking for, the value of r for that point, is also a radius of my sphere, whose radius I know. Right? So that value of r is a. And that gives us that upper bound. Everybody happy there? Everybody see what happened? Okay. So, as per usual, we looked at our theta bounds. We fixed a value of theta. Now we're going to, we've already, for that theta slice, looked at our r bounds. Now we are going to also fix a value of r. We are now then focusing on this cross-section of our cross-section, our slice of our slice. This represents a given value of theta and a given value of r. And on that, I now have to ask about z. Lowest value of z, that point. Lucky with the geometry, it's in the xy plane, sort of obvious that that's where z equals 0. Got to take the wins when you get them. The upper bound for z comes from this point. And here's where we are going to have to do a little bit of actual work here. So that point, what can I say about that point? Well, it's on this surface. It's on my sphere. What's the equation for the sphere? Well, I mean, you can write that down in rectangular coordinates, right? X squared plus y squared plus z squared and all that. Convert that into cylindrical coordinates and you get that. At which point, I think it's a very prudent move to remind yourself, wait a minute, why did I write this down in the first place? Right? You don't want to accidentally solve for the wrong variable. Recall that we are looking for a value of z. Right? We're trying to find the upper bound for z. So within this equation that we found, we need to solve for z. And that gives us our upper bound for z. Everybody happy? Okay. Same thing if you slice in the other order. Now notice this is the exact same question. I've got the exact same half ball there. And let's see here. I am just now going to do my z slicing on the outside. That gives me slices that look like this. I'm going to let you all think through most of the details here. You know, where does z start? Where does z end? et cetera, et cetera. Where it gets interesting is when you are trying to find the inner bound, the upper inner bound, right? So for R, and it's going to come from this point. And what do we know about that point? Now here's where things get a little strange. It's on the sphere we already talked about. It has the same equation that we already talked about. A lot of students would get a little overconfident here and say, oh, shoot, I've been down this road before. It's probably the same as in the previous example that we just looked at. But it's not. Here's, again, you've got to be careful. Notice here what I am interested in is a value of R. R is my inside variable. I'm looking for an R bound. I need to solve for R in this equation, not Z. I'm going to solve for R. And that gives me that as my upper bound for R. Is everybody on board? Everybody see how that, just that little tiny, critically, but tiny little bit different. Okay. All right. Okay. Okay. Spherical coordinates. Not that different from cylindrical coordinates. Different geometry, right? But again, with the conversion formulas, change of variables function. Again, with the stretching factor and the pullback, and it's all kind of the same. And again, I don't want to have to pull back and then deal with the very challenging geometry over here of what does that look like, just so that my slices will look nice and flat like this. I don't think that's a good trade-off. The geometry is sort of too hard. I think it's much nicer to just understand what do these slices look like over here in XYZ world, where I already know what my solid looks like. Well, let's just do the appropriate sort of adapted slicing, appropriate to what coordinate system I'm using, on the solid that I already have. So, okay, well, theta slices, we already know. Theta slices look kind of like that. Doors hinged on the z-axis. It's the same theta. It has the same slices. Gets a little different when you look at the other variables. And you just got to kind of draw the pictures and think it through. Phi slices. Constant value of phi. Constant angle off of the z-axis as measured from the origin gives you a cone, which is a weird thing to call a slice, right? I mean, that'd be, I'm not a good enough of a chef to make a cut like that, right, with any kind of a knife that I have access to. And then even weirder, row slices. Constant value of row. Constant distance from the origin, then, in the XYZ world. And I definitely can't do that. The only thing I could do, again, I'm thinking a melon baller would do that, right? But no knife that I know of. So this is what the slices look like, and just like with cylindrical coordinates, the good news is I'm actually not going to need any of this right here because we are always going to slice in a very particular order. Spherical coordinates has this wonderful convenience that in practically every case that I can think of, always this order. D rho d phi d theta. Just always use this order. You can't go wrong. This is always the right answer. In my entire physics major, I never saw an example where any order other than this was the better choice. It's just, this is the way you want to do it. Okay. Also, just like cylindrical coordinates, you don't want to write that down by itself. It doesn't mean anything by itself. dV requires the stretching factor included as well. So this thing by itself is, I'm going to say, kind of unnatural. D rho d phi d theta has nothing to do with dx dy dz. It's not the same thing. Dx dy dz is this whole green deal that has the stretching factor inserted there as well. So write this down all at once. That's what dV is. And furthermore, writing it down all at once, you already didn't forget your rho squared sine phi. So easy to forget. Again, so many students, understandably, forget, right? But it's points, and you don't want to leave those points on the table. And again, reminder, if you find yourself with only seconds left to go in the exam, and you didn't even have time to start the question about the spherical coordinates integral, just write this down. Points, right? So this is a good thing, not a bad thing. Okay. All righty. Let's see here. There we go. Okay, so let's see an example. Here we have a ball. It's not centered at the origin, you'll notice. It's kind of sitting up on top of the origin, like so. That being said, the theta slices are pretty easy to see. My theta slices look kind of like this, and you can see how that's what they would look like. I'm going to say all the way around, so 0 to 2 pi. Just like I was doing it in cylindrical coordinates, it's just that we're going to chop this up now in a different way. But the theta is just like in cylindrical coordinates. Okay, now I have a kind of a personal hack that I like. I find this very helpful. Looking at this cross section made by this plane, we have a kind of a weird perspective problem. You'll notice that, let's see if I can, there we go. Okay, notice that even though this plane is visible, it's kind of distorted by our angle, our perspective. In particular, notice that this right here is actually a right angle, but the way it looks on the page, it looks like obtuse. That's just because we're looking at it from some weird sort of perspective. It's just everything's distorted and doesn't look right. So I find it helpful, and I found that a lot of other students find it helpful to just redraw that picture. It's the same thing. Nothing's really happening here. We just redraw that picture, and now that right angle actually looks like a right angle. And then it's just easier to see what the phi angles are, and that'll help you get the right answers for your phi bounds. Not required, just a suggestion. Okay, so with that noted, let's think about our phi bounds. Phi starts straight up. Our phi slices go like this. Keep in mind, phi slices always come out of the origin. And they just keep getting smaller and smaller, and then it gets really confusing to see what's going on down there because, again, I'm kind of looking at the wrong picture there. So let's come over to this picture where I can blow things up. And, again, there's phi equals 0. And as phi increases, these slices get smaller and smaller and smaller and smaller. They never really quite go away until you get to all the way down to horizontal. So phi, for this theta slice, phi starts at 0 and ends at pi over 2. Yeah?
Why are you calling it the r-axis there?
Oh, yeah, that's just sort of looking at how this sits in, why is this not, there we go. Looking at how that thing fits over in this world over here, keeping in mind that's what it is. I mean, this is what we're really looking at. There isn't really an r-axis, but this direction is a direction which, at least in cylindrical coordinates, keeps z constant and it keeps theta constant, and only r is increasing. And so I could say this. This is the direction that the r standard basis vector points. Right, if you remember all that standard basis vector stuff. So it's a little bit of an abuse, it's a little sloppy, but it's just intended as a sort of a helpful guide, that's all. Yeah. Everybody happy with that? Okay, so our phi bounds, 0 to pi over 2. And now with the phi bounds identified, all we have to do is think about rho. And so for this, let's see here, for this phi slice of my theta slice, rho starts at that point where it's sort of obviously 0. Again, you get some freebies sometime. Like, capitalize when the geometry is easy. Easy money. The ending value of rho, and again, here's where you have to do a little bit of work. That ending value, that last row slice, is on this curve, which we don't immediately recognize until we come back up here and remind ourselves that it came from that being part of our sphere. So what you have to do is take this sphere of radius A, centered at 0, A, write down the rectangular equation for that sphere, and then convert that rectangular equation into spherical coordinates. And this is what you're going to get when you do that. Please do make sure that you can actually do that. It's all stuff from Chapter 1, and that then gives you your upper bound right there. Okay, all right, so we'll pick up here next time. See y'all later. Have a good rest of your Wednesday. See you Friday.